black holes, one of the most baffling and strange phenomena in the universe, remain the focus of intense examination and interest among space experts and physicists alike. These celestial objects, characterized by their enormous gravitational levitational pull and the complete lack of illumination or emission, represent a limit that cannot be exceeded. The known laws of physical science no longer apply. First speculated by Albert Einstein in 1916 as a direct result of his theory of general relativity. Black holes were only conceptual. Until technological advancements in the 20th century allowed for their indirect detection. The pivotal moment occurred during the 1960s, when researchers studying the Cygnus constellation accidentally discovered an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star's orbit around an invisible partner defied conventional explanations until it became clear that it was in a gravitational relationship with a massive black hole, Cygnus X1. The discovery of Cygnus X1 provided crystal clear evidence that black holes exist and marked the beginning of a new era of research into these cosmic enigmas. Cygnus X1, located about 6,000 light-years from Earth, is incredibly dense and possesses such a powerful gravitational force that it cannot let go of anything, not even light. It got its name because of this distinctive feature, a black hole that holds the essence of these enigmatic objects. Following research has uncovered a variety of black holes scattered throughout the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million black holes. Despite their elusive nature and the difficulty of direct detection, astronomers have identified numerous candidates in our galaxy, ranging from stellar mass black holes, formed from the remnants of massive stars, to supermassive black holes, located at the centers of galaxies. The weight of black holes in space and time goes far beyond their immediate vicinity. They influence the course of cosmic structures and impact the fate of objects that venture too close, determined by their immense gravitational pressure. Objects are drawn inevitably toward the event horizon, the final boundary, where they are subjected to extreme tidal forces and are eventually consumed by the singularity at the center of the black hole. This disastrous interplay, known as extreme spaghettification, is a manifestation of a black hole's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes stretched to an extreme degree and twisted into spaghetti-like filaments. The forces emanating from the black hole overpower the internal bonds holding the object together, causing it to disintegrate into a stream of matter that, in the end, merges with the singularity. Despite their attraction as research laboratories for testing the limits of physical theory, black holes remain shrouded in intrigue. The search for the truth about them continues, driven by a desire to comprehend the basic nature of space-time and gravity itself. In the vastness of the universe, black holes stand as silent, beckoning sentinels, inviting humanity to investigate the depths of the unknown and expand the boundaries of human understanding. Despite the enormous distance between us and the closest black hole, roughly 1,500 light-years, questions and concerns regarding their potential effects continue in 2021. Researchers achieved a monumental accomplishment by securing the first clear image of a black hole, specifically M87, located at the center of the Messier 87 galaxy. This remarkable achievement provided critical information about the nature of black holes and their elusive structure. The visual data revealed that the layers of black holes are intricate, challenging the traditional perception of them as distinct voids of nothingness. Through thorough investigation and advanced imaging techniques, scientists uncovered 3 distinct layers inside: 1, the event horizon, the outermost layer, and a critical boundary, marking the point of no return. Once an object crosses this threshold, the forces of gravity become insurmountable, ensuring its inevitable fall into the depths of the black hole. 2, the photon sphere, the second layer, where light itself orbits the black hole. Any photons captured here are trapped indefinitely. Victims of the immense gravitational pull. Point 3. The singularity, the third and final layer at the heart of the black hole, where the laws of physics break down. The well-known rules that govern the universe cease to apply, plunging researchers into a profound realm of speculative theories. Uncertainty. The complexity and variation of black holes presents significant obstacles to our understanding, while they share a common structure of 3 layers. Each black hole possesses distinctive characteristics and behaviors that defy easy classification. As a result, conventional methods of scientific inquiry often prove insufficient, requiring creative, indirect approaches to solving their mysteries. Observation remains the primary means of studying black holes. Direct investigation is impossible, due to the immense barriers posed by their gravitational forces. Any attempt to explore a black hole would result in destruction, crushed into obscurity by the ferocious forces at play. Despite the efforts of researchers, many questions remain. Numerous hypotheses, ranging from the collapse of massive stars to complex cosmic dynamics, offer intriguing hints about their origins and behavior. Notably, NASA's study of the cosmic center of M87 revealed compelling evidence of a supermassive black hole, exerting gravitational influence over vast cosmic scales. Despite these difficulties, the pursuit of knowledge continues unabated, motivated by humanity's inherent curiosity and thirst for understanding. While the mystery of black holes may defy simple comprehension, the unwavering commitment to scientific investigation promises to illuminate even the darkest corners of the universe. Unraveling the profound secrets hidden within. Roy Kerr's groundbreaking 1963 work provided a new model, shifting perspectives on black holes. He proposed a revolutionary theory of rotating black holes that defied conventional concepts. Central to Kerr's model was the concept of the ergosphere, region surrounding the black hole where opposing forces work together to prevent matter from collapsing further. This new domain represented a departure from conventional physics, pointing to the vast mysteries still hidden in black holes. Perhaps the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This theoretical structure represents a potential gateway through space-time, possibly serving as a link between the farthest reaches of the universe or even its parallel universes. The idea of wormholes stems from the intricate interplay between our description of reality and the theory of general relativity proposed by Einstein. Within this framework, existence is woven together into a quadrilateral fabric known as space-time, and massive objects warp this fabric, creating gravitational fields that affect everything around them. The movement of wormholes in the surrounding material basically serves as a quick route through the cosmic fabric, connecting distant points in space-time and possibly facilitating rapid traversal across vast cosmic distances. However, the practicality and stability of wormholes continue to be the focus of intense theorizing and discussion among theoretical physicists. Despite the fact that wormholes present enticing possibilities for interstellar travel and significant time manipulation, research limitations and difficulties temper these fantasies. The intrinsic instability of wormholes, combined with the formidable barriers posed by quantum forces and radiation, raises questions about their feasibility as viable means of transport. In addition, Einstein's general relativity theory imposes fundamental limitations on how fast movement throughout space can occur, implying that even if stable wormholes existed, they might not allow travel faster than light. Traveling at light speed remains a key concept in many sci-fi narratives. Despite these impediments, the enticement of wormholes persists as an example of scientific curiosity and an ongoing investigation into alternate cosmic portals and realities. The idea of the wormhole, named after its pioneering scholars, exemplifies the enticing promise of access to other dimensions, inviting humanity to contemplate the mysteries of the universe and the unending possibilities beyond, on the search for a unified theory that reconciles gravity, which governs large-scale structures like black holes, and quantum mechanics, which governs the behavior of particles at the smallest scales, has spurred the hunt for a theory of everything. This is a comprehensive framework that can incorporate all fundamental forces and particles in the universe. Expert insights, theories, and debates stand at the forefront of this endeavor. Renowned theoretical physicist Miyoku's groundbreaking work has propelled the investigation of superstring theory. Offers one such promising approach. String theory represents a dramatic departure from conventional models, assuming that fundamental particles are not point-like entities, but rather microscopic, vibrating strings. These strings, like those of a musical instrument, vibrate at particular frequencies, which give rise to the different forces and particles found in nature. In this paradigm, the universe is transformed into something like a great orchestra, where each particle corresponds to a distinct harmonic resonance. One of the most striking ramifications of superstring theory is its capacity to explain mysterious events associated with wormholes, black holes, and other exotic solutions too. Einstein's equations. As strings move through the fabric of space, their fluid movement may lead to the development of gravitational singularities and topological anomalies. However, the elegance of superstring theories conceals their inherent complexity, as they require the presence of additional dimensions beyond the familiar three spatial and one temporal dimension. These extra dimensions, though imperceptible to direct observation, pose a challenge to human intuition. Nevertheless, applied models such as the analogy of fish in a lake who can only perceive two dimensions offer glimpses into these higher dimensional realities. The consolidation of these extra dimensions, akin to folding a sheet of paper into a tight roll, renders them imperceptible at everyday scales. Still, their influence permeates the very fabric of reality. The exact nature of these hidden dimensions remains conceptually obscure, but a promising explanation may lie in their presence, being essential to the complex structures and anomalies observed in the universe. Furthermore, the mathematical foundations of superstring theory have sparked a revival in theoretical physics and mathematics, demonstrating profound connections between dynamic mathematical patterns and physical phenomena. In fact, the search for a theory of everything acts as a catalyst for the unification of diverse scientific fields, shedding light on the deep interplay between mathematics and the natural sciences. Despite its scientific precision and theoretical elegance, superstring theory remains an untested framework in need of empirical validation. The elusive nature of extra dimensions constitutes a formidable obstacle, relegating the theory to the realm of mathematical speculation. Nevertheless, the daring vision of superstring theory continues to captivate the minds of enthusiasts and researchers alike, enticing them on a journey of intellectual exploration. As we expand our understanding of theoretical physics, we are guided by the illuminating beacon of the universe's mysteries. Poised at the threshold of a new era of comprehension and insight, the task of unraveling the secrets of quantum black holes has long perplexed physicists, representing a significant challenge to our understanding of the universe's fundamental nature. Despite numerous efforts to solve this riddle, the answer has remained elusive. Edward Witten of the Institute for Advanced Study in Princeton once described superstring theory as a modern form of physics that emerged almost by accident in the 20th century. However, recent advancements have injected new hope into the quest to understand quantum black holes. Several groups of physicists have independently reported substantial breakthroughs suggesting that string theory could offer a comprehensive solution to the problem, albeit within the more restricted setting of two dimensions, rather than the full 10-dimensional model proposed by conventional superstring theory. This is an encouraging development, though the quest for a complete resolution remains ongoing. The complexities of the situation present substantial challenges. Still, the search for a theory of everything calls on us to investigate the deepest recesses of cosmic existence, where the boundaries between reality and theory blur. and the secrets of the universe await discovery. Black holes carry profound implications for our understanding of the cosmos, challenging our ideas of reality and raising existential questions about the nature of existence itself. The interplay between black holes and other astronomical phenomena such as neutron stars and gamma ray bursts reveals the intricate processes at work throughout the universe.